In the realm of physics, classical mechanics has long held sway as the foundation upon which our understanding of the physical world was built. From the groundbreaking work of Sir Isaac Newton to the revolutionary insights of Albert Einstein and countless others, this discipline has shaped our comprehension of motion, force, and energy. The following list delves into the key principles, laws, and concepts that have defined classical mechanics and its evolution into the quantum realm. Together, these ideas have not only guided the development of technology, but also illuminated the inner workings of the universe. Einstein's theory of general relativity, proposed in 1915, challenged classical mechanics by introducing curved spacetime. The uncertainty principle, put forth by Werner Heisenberg in 1927, undermined determinism in classical mechanics by stating the impossibility of simultaneously determining a particle's exact position and momentum. Newton's laws of motion, published in 1687 by Sir Isaac Newton, form the cornerstone of classical mechanics. The conservation of angular momentum asserts that the total angular momentum in an isolated system remains constant unless subjected to external torques. Classical mechanics falls short in explaining subatomic particle behavior, leading to the emergence of quantum mechanics in the early 20th century. The principle of least action, initially proposed by Pierre-Louis Maupertuis and further developed by Euler and Lagrange, asserts that the path taken by a particle between 2 points minimizes its action. Hamiltonian mechanics, formulated by William Rowan Hamilton in the early 19th century, offers an alternative mathematical framework to Newton's laws. The equivalence principle, postulated by Albert Einstein, suggests that gravity's effects are indistinguishable from acceleration. Hooke's law, formulated by Robert Hooke in the 17th century, describes the relationship between spring force and displacement. Classical mechanics encompasses subfields that address the behavior of solids, liquids, and gases. Quantum field theory, QFT, becomes relevant when classical or quantum mechanics alone cannot explain phenomena, particularly at the quantum level with high speeds. The term classical mechanics was coined in the early 20th century, building upon Johannes Kepler's earlier astronomical theories. Isaac Newton's three laws of motion, first published in Philosophiae Naturalis Principia Mathematica in 1687, serve as the foundation of classical mechanics. Kinematic equations elucidate object movement without considering causes or effects. The conservation of momentum is a fundamental principle stating that the total momentum of an isolated system remains constant. The conservation of energy is another fundamental principle asserting that the total energy of an isolated system remains constant. Pendulums exemplify classical mechanics principles, including energy and momentum conservation, and force-mass acceleration relationships. Gyroscopes demonstrate classical mechanics concepts, such as the conservation of angular momentum and precession. Kepler's laws of planetary motion, discovered by Johannes Kepler in the early 17th century, describe planets' elliptical orbits around the Sun. Escape velocity represents the minimum speed required for an object to overcome a celestial body's gravitational pull. The center of mass denotes the point where a system's total mass is evenly distributed, remaining at rest even if individual objects within the system move. The moment of inertia quantifies an object's resistance to rotation, depending on its mass distribution. Torque measures the rotational force on an object, equal to the force applied multiplied by the distance from the axis of rotation. Angular momentum characterizes an object's rotational motion, equal to the moment of inertia multiplied by angular velocity. Work equals the force applied to an object multiplied by the distance it moves in the force's direction. Power quantifies the rate at which work is done, calculated as work divided by the time it takes to complete the work. Simple machines, including levers, inclined planes, wedges, screws, wheels and axles, and pulleys, facilitate work. Machines transfer energy between sources, amplifying force, altering its direction, or changing its type. The legacy of these concepts extends far beyond the pages of scientific textbooks. They are the threads that weave through the tapestry of our understanding of the physical world, connecting past and present, theory and application. From the elegant simplicity of Newton's laws to the mind-bending implications of the uncertainty principle, classical mechanics continues to inspire wonder and discovery. And so, as we move forward in our quest to unravel the intricacies of the cosmos, we do so with a profound appreciation for the enduring wisdom of classical mechanics.